So, as I said, what I'm talking about today is what we study about old earthquakes using photogrammetry, so satellite stereo imaging, and early seismograms. This is sort of a novel combination that we're bringing together, and I'm going to talk about some of the examples of what we can do combining these two techniques. The work that I'm talking about here involves a lot of other people, including, I'd like to give particular acknowledgement to Galina Kulikova at the University of Potsdam, who has developed a lot of the seismological techniques that I'll be introducing later on in this talk. Of course, the rest of the group here, my supervisors and colleagues, other postdocs I've worked with, as well as students, and international partners that I've been working with in Kazakhstan, Kyrgyzstan, and China to help do the field components of this research. So research, my component of COMET research is focused on earthquakes. And so an important place to start is with a map of earthquakes around the world. Clearly this distribution of seismicity is a relatively old map, but it's representative of where earthquakes happen. In fact, around the planet, you can see that they highlight plate boundaries, but there are important zones outside of the plate boundaries where lower densities of earthquakes sort of fill out these continental interiors. In fact, those regions show up quite well when the global GPS network or strain mapping, in fact, strain mapping, like other researchers within COMET are doing in continental interiors. These other zones are highlighted by slow deformation that's still high enough to produce earthquakes every so often. These end up being quite high hazard areas. I'm going to focus on one of the broadest ones. So looking at earthquakes in Central Asia, part of the reason for this is that this is a zone of deformation thousands of kilometers across, far from any plate boundaries, and of course it's perplexed and intrigued scientists and spawned tons of debate over decades as we've understood and come to question and further understand tectonics. When you look at areas like this, one of the motivations of some of the research that we do here within COMET and its partner projects, the Earthquakes Without Frontiers and looking inside the continents from space, are motivated by the extremely high risk posed by earthquakes in these areas. Because they're infrequent, people are often not prepared. It's not part of necessarily the regular life cycle, the way they are in plate boundary countries like Japan, Indonesia, and Chile. So continental interior earthquakes tend to result in huge numbers of deaths, and they're rare and thus difficult to study and difficult to understand. So what we want to do is try and improve our record of these earthquakes, however we can. One of the reasons that they are so infrequent is that in this broadly and slowly deforming region, a huge number of different faults take up the strain that's being accumulated. So this example across the western Tien, Shan, mostly in Kyrgyzstan, shows the gradient in crustal velocities expressed as these GPS vectors. And in the middle there is a map, a detailed map by Steve Thompson, early 2000s, of active faults in this region. And it's representative of this and other surrounding areas, showing the vast number of faults that are there to accommodate this relatively slowly accumulating strain. So although the whole region is deforming quickly, on any given fault, the recurrence of earthquakes is extremely infrequent. This is what makes it so dangerous. And this is what makes it most important to understand how all of these faults work together to produce the suite of earthquakes that threaten a region like this. Fortunately, in Central Asia and this broad deforming region around the Tibetan Plateau, the landscape is dry, relatively arid. And this helps preserve earthquake ruptures that have happened in the past. And so we do have the opportunity to go back and look at a longer record of earthquakes than in many other parts of the world. The image that I show here, lost in this landscape of that's covered in silt coming off of the deserts, is a fault rupture that runs through it. When I take off this line, you can now see it delineated quite clearly. I'll use this rather than the laser line. So the fault that runs through here was produced by one of the earthquakes that I'm going to be talking about later, and I'll show many more examples how we've come to monitor it. But the reason this is a valuable place to study earthquakes, it has a long historical record thanks to trade routes, dense population along these trade routes, and then the documentation that comes along with having these long established trade routes. It's also an arid environment, and then the alien silt that you see pictured here, that comes off of the desert, forms a really good datable material that we can use to assess the timing of previous earthquakes. And so it ends up being a really nice laboratory for understanding the history of events that have happened here. The other benefit of this region is that it's had a large number of earthquakes in the historical period that have been documented by people, eyewitnesses of those events. But in particular, I'm going to be focusing on some earthquakes that were also instrumentally recorded in the early days of instrumental seismology, using seismometers that look like this. These are quite different from what you see these days, including, if you follow me on Twitter, you've seen the little raspberry shakes, these little nice plastic, compact, small devices. Modern seismometers are little electronic things that are encased in sort of small containers and barrels. This is roughly my height, and it's a several hundred to 1,000 kilogram mass suspended above a rocking pendulum. These are early seismometers from around the turn of the last century, and a bit later. And I'm going to show you some of the records that we derive from these and how we can revisit what they recorded. So what can we learn about these earthquakes? Why are they important? Like all global earthquakes, the earthquakes in the Middle East are tragic but full of lessons. We want to know how large they are. Can our observations of surface faulting refine estimates of their magnitudes in order to understand how large potential earthquakes may be, how often they recur? We also want to understand what kinematics these individual earthquakes had. Because of this large, vast network of faults, it's important to understand how individual earthquakes contribute to the overall strain that accumulates in one of these deforming zones. Vice versa, how does the strain that's imposed upon the region manifest in individual earthquakes? And so we want to understand how the individual earthquakes relate to the larger deformation in order to understand in both directions. If we can measure the displacement fields and crustal velocities, what does that mean for earthquake hazard? I'm also going to talk a lot about the complexity of these fault systems. And the real question here is, how did rupture propagate through these complex fault systems? I'll go into a little more detail about that momentarily. So what I'm going to do here, I'm going to introduce the earthquakes that I'll be talking about. I'm going to ask about what I'm going to convey to you what we want to understand from these earthquakes. I'm going to talk through the methods that we use to understand them, including the satellite DEMs to get high-resolution topography and the digital analysis of these old analog instrumental seismograms. These are the two earthquakes that I'm going to be focusing on. We're back looking at this broad deforming region, largely the Tibetan Plateau and Tien Shan mountain ranges. One of them was a really early earthquake in 1889. It's one of the largest earthquakes ever recorded within the continents, away from subduction zones. In 1932, there was a magnitude 7.6 earthquake that's fairly well documented in ways that warrant further scrutiny, as I'll describe. This is the Changma Earthquake in Western China. So to take an aside here on what's important about understanding the nature of these fault ruptures and why we want to document them in detail, both in the landscape and seismically, is that when we try and understand earthquakes, we have a relatively simple conceptual framework that we use for them that relies on a few simple parameters. The size of an earthquake determined by the length of the fault that ruptures, the width, so together that's the area of the fault, and the amount of displacement that goes on during the earthquake. Together, these quantities define the size of an earthquake rupture. They also, based on some simplistic assumptions, help define the average recurrence, or if you know the magnitude of an earthquake, given a particular budget of strain or slip accumulation, you can work out how many of these earthquakes are going to happen in a particular amount of time. The problem is that when earthquakes actually happen, there's a tendency to violate these pretty simple premises about what an earthquake should look like in its simplest form. Plenty of earthquakes may be quite simple, but especially away from the big plate boundaries, you get very complicated earthquakes. One of the first really well-documented examples of this was the 1992 Landers earthquake that you see the surface trace map of pictured here. Anyway, in the middle of the slide. This earthquake ruptured a large number of different faults that combined together to produce a larger earthquake than was expected from any single one of those faults ruptured. Subsequent examples in Southern California and elsewhere have shown the same thing. So the Cucapá, Mexico earthquake in 2010, the Darfield, New Zealand earthquake also in 2010, and most recently, and sort of most astonishingly, the Kaikoura earthquake in 2016. This earthquake ruptured literally dozens of different faults and produced a much larger earthquake than we would have expected from any one of these faults individually. It also assembled together a great number of faults that we wouldn't necessarily have thought would all be involved in the same earthquake. In fact, of course, an even more recent example than this was just earlier this month in Southern California, the Ridgecrest earthquake. The mapping pictured here is by Chris Milliner at JPL, what you can see from this, which is measured by really rapid response satellite deformation fields and high-resolution imagery, is the vast number of faults, fractures, and fault zones involved in this, meeting each other at high angles, branching, anastomosing, and interestingly, in this sequence of earthquakes, there are important questions about whether these faults ruptured and then re-ruptured. There's a great deal of complexity in even a relatively simple earthquake. But essentially, this is why we're going back to try and see whether this behavior, which we're recognizing when these earthquakes happen these days, we tend to be surprised by them. Kaikoura was this big surprise of an earthquake. The Ridgecrest earthquake strung together a lot of small faults that were not a continuously mapped structure. So in this sense, these earthquakes surprise us. But as I'm going to show you, it's not particularly new behavior. And so we can find examples in the past that are illuminating for understanding how things like this happen now, and how you get the really large earthquakes that we see. So one of the frameworks for dealing with this issue of the complex ruptures that are beyond just a simple planar fault rupturing and slipping a finite amount are that in modern, in sort of cutting-edge modern seismic hazard models like the Uniform California Earthquake Rupture Forecast, the solution to resolve what the hazard of earthquakes is to work out how often any given portion of a fault participates in earthquakes with any other. And so that's the way that the USERF model approaches the seismic hazard problem. It's trying to understand how much these faults interact, not just how much the fault as a whole contributes to the seismic hazard budget. So we want to understand, how do faults in fact interact? And the more examples we can get of this, the better our understanding is going to be. So the examples that I'm looking at are in, as I've described several times, in Central Asia. The series of earthquakes that I want to highlight are around the turn of the last century, the northern Tien Shan. Here we're looking at the border between Kazakhstan and Kyrgyzstan. Kyrgyzstan broadly down here, Kazakhstan up the steppe land above to the north. This series of earthquakes around the turn of the century propagated along this fault system, or sort of a sequence of them happened and severely damaged the rather large city of Fernie, which is now Almaty. in Kazakhstan. And at the time, these earthquakes were actually fairly well documented. I'm going to focus on the two largest of them, the 1889 Chilik earthquake, magnitude 8.3, and the 1911 magnitude 8.1 Chon-Kemin earthquake. The reason to focus on these are some photos of the damage that each of those did, or that the 1911 earthquake did in, well, that's both earthquakes, in the city of Berni, Almaty. The church stands today. These two earthquakes, I'll show the isoseismal map. So this is showing the distribution of shaking intensity. The 1911 earthquake was well documented by intensity reports and subsequent field surveys that identified where the faults were that ruptured. The 1889 earthquake was a bit more sparsely defined, and at the time, surveys were not conducted to identify which faults had ruptured. This was essentially before the days that scientists recognized that fault rupture is what produced earthquakes. Subsequently, I'll show what our subsequent research has done. This is the documentation of the 1889 earthquake by eyewitnesses, showing intensities concentrated in a. You can imagine. Sorry, I'm shining the laser instead of using the mouse here. You can see this rough bullseye pattern centered with the highest intensities around a particular area near the north shore of Lake Issyk-Kul. For many decades, scientists tried to identify the source of this earthquake, and only recently, well, in the last couple decades, has it really been defined. In contrast, the 1911 earthquake, 2 decades after this and nearby, was visited in the field in the years following the earthquake, identified and mapped in great detail. So what you see up here is a map of the ruptures in 1915. Subsequent mapping has gone out and proved the identification of the faults that produced that earthquake. That itself is a relatively complex earthquake rupture, but I'm not going to focus it on much here. Several other groups have done research on that, but it serves to illustrate that the earthquakes in these zones can be really complex, involve multiple different faults with different kinematics. Part of the reason to highlight that earthquake, though, is that it formed one of the seminal cases that helps develop this, that helped Galina Kulikova, University of Potsdam, who I mentioned before, develop this technique for analyzing the early paper seismograms. I'll describe the technique in more detail later, but it's worth highlighting here that the great deal of effort that goes into digitizing and analyzing these relatively non-digital, non-modern records. They have a great number of artifacts that become problematic and need to be dealt with. And this earthquake in 1911 was one of the first ones to be robustly enough recorded around the world that it could be evaluated and serve as a test case for some of these methods of evaluating the full waveforms on early seismograms. The earlier earthquake, the 1889 earthquake, was also recorded by dedicated seismic instruments, one in particular, and it actually amounts to one of the first recordings in the world of an earthquake by a dedicated seismometer. This was a horizontal pendulum. It was installed in Germany, and you can see the record of the earthquake here. It's shown on the full record is shown on the lower panel here, and this is a schematic showing the sort of envelope of the waves. You can't see the individual wiggles because the way that it was recording basically didn't permit that. Furthermore, this earthquake was so large that even though it happened that all the way in Germany, it sent this poor delicate instrument off the scale. And so the only part of the earthquake that's recorded is the coda here, just the tail end of the seismic waves. Not any of the real important information about the source that you get here. Nonetheless, Galina Kulikova and Frank Kruger were able to evaluate this, especially in comparison to the nearby 1911 earthquake, and assess a magnitude for that event. It was also recorded by non-dedicated seismometers, so instruments, other mechanical instruments that were set up in observatories that didn't actually form part of a dedicated seismic network, but were measuring other things. So these magnetometers at British observatories also had a mechanical response to the passing seismic waves from these huge earthquakes. And the comparison of recordings in 1889 and 1911 allowed Galena and Frank to evaluate the relative magnitudes of the two earthquakes, which led them to the conclusion that the 1889 earthquake had a magnitude of about 8.3. This is actually a problematically high magnitude. And so what we've done subsequently is gone out to the field and tried to understand what faults in the world that hadn't really been found had come together to produce this massive earthquake. So the earliest reports of ruptures from it were from the 90s, where a scarp was identified in southern Kazakhstan, pictured here in this satellite image. The team from Oxford subsequently has gone out and mapped and measured this scarp, both in the field with low altitude photogrammetry using drones and balloon surveys. And the team also excavated a trench across the fault to measure to measure the date of the rupture and find any subsequent other events. You can see the height of this here, and this is in fact a single event scarp, where the downthrown side of the valley, the downstream side of this stream channel that I'm standing in is upthrown relative to the upstream side of it. So the fault runs along like this. Sort of overlaid on it, this is a figure from the paper that reports the trench reversed so that you can sort of see how it fits there. It's a 5,000-year-old surface overriding basically medieval age sediments. So it did happen sometime in the last 400 years. It's a pretty strong candidate for this 1889 rupture. You can go out and trace that scarp along strike, make measurements of the offset all along, and we get values of sort of 6 to 10 meters, which is quite large for a single event, but within the realm of historical precedent. All of that was this small reach of the fault right in here, which alone is certainly not enough to produce a magnitude 8.3 earthquake. So the question arose, what other faults around appear to have fresh rupture on them? Some faults farther in the mountains show small scarps. Some faults to the north on this mountain front show relatively fresh scarps that you can see here. So this has allowed us to expand and map out the rest of the fault. One of the ways that we're able to interrogate this, though, is using high-resolution elevation models. And in particular, one of the ways that we identify these scarps, especially high in the mountains up here, is through these high-resolution topography. The way we do this is using stereo imagery. So as a satellite passes over the surface of the Earth, it takes images from different vantage points. And as it passes over, these different vantage points give you a sense of the three-dimensional structure of the landscape. We can evaluate that. There are now, with modern computational capacity, it's relatively trivial to put those together and calculate an actual topographic surface at nearly the image resolution. This is a DEM that we constructed, a digital elevation model that we constructed of the topography around the suspected ruptures. And I'll show you an example where you can see one of these ruptures slicing across the landscape here in this topography. So making these high-resolution topographic maps is what enables us to trace out these historic ruptures and the single event scarps that they created in the landscape. Now, one of the things we can do once we have the high-resolution topography, beyond just mapping out the trace of the fault, is actually understanding the amount of slip in the fault. As I showed you earlier, we've measured the offsets using balloon and drone photogrammetry. course, we can do the same with satellite photogrammetry, and it's important in particular cases like this. What I'm showing you here, this is a scarp running through a valley in the mountains of southern Kazakhstan. It's actually this portion of the fault on the left-hand side of the image here. It's fairly well understood that the Tien Shan is the shortening across the Tien Shan is in part accommodated by a set of conjugate right and left lateral strike-slip faults, in addition to the reverse faulting that's nearly north-south oriented. The question was, what does the fault over here? Is that part of this fault system, the left lateral fault system, or the right lateral fault system, or is it part of a different sort of reverse faulting system that's running anomalously through the mountains? Here you can see the scarp in the hillshade of the elevation model, but it's unclear, based on the slope and the scarps that you see here, what the sense of motion on this rupture actually is. So we went there in the field a few years ago to take surveys ourselves and measure these. And what I want to highlight is that without knowing the sense of motion on this fault, nor strictly the dip of this fault, strictly measuring profiles across it is not going to give you a meaningful answer about with the slip vector, the offset in the earthquake. You can imagine planes, the alternative scenarios where this is a if the dip of this fault varied, the scarp that you see at the surface would represent very different amounts of offset. So it's important to be able to constrain that somehow. In these cases, when the kinematics of the fault are unknown, profiles are really problematic, and so we needed another way to measure the offsets. This led Dave McKenzie and I to develop this method of taking corresponding components of different offset landforms and combining them to get a three-dimensional slip vector. So the idea is that if you have if you have a series of offset landforms, say for example these ridge lines, the sun angle shining on them like this, so this is sort of facing down slope this way, this is relatively level, this is facing down slope this way, this is facing that way. That corrugation of the landscape allows you to reconstruct the full landscape instead of just measuring single offset piercing points along the scarp. What we end up doing using the method that we developed, is that once you take all these corresponding portions of the landscape together, analyze them together, we find that there's actually more right lateral slip than vertical slip here. So it's a rather unintuitive result when you look at the picture that we saw. Imagine the sense of apparent offset that you see here. If you suspect that it comes from lateral motion, you would presume that it's left lateral motion, with the side of the fault that Ramon Aerosmith is standing on here moving off away from you, left laterally. In fact, what we find is that there's a big vertical component that swamps an apparent right lateral sense of motion, well, an actual right lateral sense of motion, giving you this uphill facing scarp. So it's important to actually evaluate the entire landscape, and that's what's enabled by having this high resolution topography. So altogether, taking that approach to looking at these offsets allows us to map out in detail these three different faults that came together to produce the magnitude 8.3 earthquake in 1889. Importantly, this zigzag pattern that they form, rupturing conjugate faults, is one of these unintuitive combinations or unexpected combinations of faults rupturing together. I think these days we've had enough examples that we're not necessarily surprised by this anymore. But it's important to recognize that this behavior may be more common than and has led to the expectations we have now. So there's a single event scarp that we kind of trace through the mountains there. Offsets range up to 6 to 10 meters. 3 conjugate faults were involved in this earthquake together. And 80+% of those ruptures are not at the mountain fronts. So they're happening on faults that are sort of buried deep in the topography, not the intuitive ones that we would expect producing the most earthquakes. This is all cautioning us about how we interpret where seismic hazard arises in these environments. I want to talk about the next example, for which we have sort of more instrumental data, is the Changma earthquake in Gansu, China. Happened on Christmas Day in 1932. It was well documented at the time by intensity reports and damage, and over the subsequent decades, it was the fault rupture was identified in the field and has been studied many times, although the results have been reported with the reported results have conflicting kinematics and descriptions of what exactly ruptured, what the nature of this earthquake was. So as I said, some of the earliest documentation of it was the intensity reports themselves. It involved damage to several of to the end, essentially this big gate at the end of the western end of the Great Wall, as well as to the wall itself. They've been repaired now in those photos. The variety of reports that have been published about this earthquake, as you can see here, show fairly different rupture maps. Everyone agrees on broadly on a network of faults that runs through the mountains with about this orientation and a number of different segments. But there's not necessarily agreement about exactly which faults were involved, nor about what the kinematics of these faults are. Importantly, one of the major Chinese report on this earthquake reports every sense of motion: left lateral, right lateral, and reverse faulting. In addition, the focal mechanism that they get for this earthquake involves either right lateral faulting on a structure that's oriented with the rough regional stripe that we see in the rupture, or left lateral faulting on on a perpendicular structure. So the original seismic interpretation is somewhat problematic, especially in regards to the regional kinematics and what's been observed from this earthquake. So we went back and obtained satellite imagery, stereo satellite imagery from the Pleiades satellite. So it's about 0.5 meter resolution with this footprint surrounding the ruptures that are identifiable. Here's what the satellite imagery looks like. Here's what the DEM that we've derived from the stereo imagery looks like. And it may be difficult to see depending on your screens, but with the elevation map, you can start to get a hint that there are these steps in the topography. And you can actually map them out in detail. The rupture is quite well preserved in the desert landscape. We'll move to the center of the rupture here, where it's actually quite exquisitely well preserved. You can see it clearly in the running straight down the middle of the image itself. Although there are features in the landscape that make its interpretation a little bit ambiguous. When you use the elevation map instead of just the imagery, you see the really nice, clear scarp of a single event, which represents the 1932 earthquake. Of course, the value in this, as I described earlier, is not just in mapping out where the fault ruptured, but in mapping out the offsets and the co-seismic slip during this earthquake. So you take profiles across the digital elevation, you can quantify the slip in the earthquake, which in this case is something like something around 5 meters at this section of the fault. The high-resolution imagery gives us the opportunity to also identify portions of the rupture that hadn't been previously identified, including this left lateral strand of the fault, which helps support the notion that there's actually partitioning of the slip. At the far end of the fault, there are longer-term offsets that accompany the the small-scale scarp that runs through this linear valley here. The large-scale offsets can be reconstructed, and the surfaces can be excavated into datable material, sampled from them, and we can get a long-term average slip rate on this, basically 4 millimeters per year. This helps us understand how the relatively contemporary earthquake, the 1932 earthquake, fits into the scheme of the long-term slip. Similar, we can take a similar approach elsewhere, looking a little bit farther west along the fault. There's at this portion of it, there's not really a lateral component. You're looking at a reverse faulting scarp. Again, you can see the scarp there in profiles across it. This is a multi-event scarp that we're looking at here, more than just the 5 or fewer meters that we were seeing in 1932. Again, we can date that and estimate the uplift or convergence rate, and the high-resolution fault mapping will ultimately enable us to document the structure of these faults and understand exactly how the uplift rates that we can measure are converted into convergence. This is a comparison. Just look, this is a photograph taken from around the southeastern edge of this map here. You can see the 1932 rupture snaking across this plane, only about a meter of slip, and then this higher scarp in the background, which is the 12 to 15 meter scarps that you're seeing back here. Much farther west, you can see both the 1932 earthquake and the larger scarp. Throughout the DEM we have from the stereo satellite imagery, we can see small scarps resulting from the 1932 earthquake. And periodically, they run along preserved paleoscarps in older abandoned terraces that have been preserved, such as this. This enables us to compare the contemporary slip from 1932, the single event post-seismic slip, with the longer term slip rates. In fact, this photograph taken at this site looking up at this paleoscarp illustrates nicely the juxtaposition of the 1932 scarp, this relatively steep, fresh, oversteepened bit of the escarpment you're looking at, and the larger scarp behind it, which is several times. At this site, we can also identify lateral offsets in the alluvial fan. And so all along this earthquake rupture, we're able to document both the uplift, the vertical offsets, and lateral offsets where they exist. What that results in is a map of some key sites showing the sense of slip along different portions of this fault. And what I want to point out about what we've calculated here is that despite the wide range in fault orientations and sense of motion along the faults themselves, the amounts of slip that we measure are roughly consistent with the same slip vector across the whole, at least the same slip vector azimuth across the whole length of the earthquake rupture. And so the different kinematics shouldn't surprise us, because this single slip vector is going to be resolved differently on faults that strike with different orientations. The question then arises, how did the earthquake rupture propagate along this fault system with different orientations, different structures? So for that, we want to turn to the historical seismology and see if we can identify, along this 160-kilometer long earthquake rupture, any signals of some progression, directivity, or subevents. Fortunately, there are a relatively large number of seismic recordings of this earthquake. Despite it being in 1932, in the nascent days of instrumental seismology, it was recorded at observatories all around the world, from which we've gone out and I've obtained copies of or paper records or scans of these original paper seismograms. This is the map here shows the distribution of instruments that were that at least have records of the 1932 earthquake on them. There were at the time more seismic stations around the world, but these are the ones, well, for which Christmas Day 1932 was still available in the archives and observatories where they found. And I've differentiated here. Once you accumulate all of these different records, some of them are no good because there are timing errors, there are other sorts of mistakes that make, and artifacts and deficiencies within these early records that don't allow you to use them. Nonetheless, I was able to collect 44 different records that are definitely usable. I'll show you a sampling of them in a moment. But I just want to point out at the moment what we can theoretically actually do with these old seismograms. So, of course, the way that they were recorded was by mechanical instruments etching out on smoked paper or on photographic paper with a small light beam. The trace of an arm attached to a pendulum and inertial mass that was able to detect long period teleseismic waves from the far side of the world. In the early 1930s, these instruments were deployed at observatories around the world, but they were being tuned and adjusted to understand just how to record this variety of earthquakes, local ones, distant ones, understanding which sizes of earthquakes could be detected by which methods, how you needed to tune and dampen your instrument in order to capture it. So there's huge variety in the quality of these records in the instrument response, and they're often a little bit sparsely recorded. So it can be a bit of a sleuthing job to understand, to try and get all these details out. Depending on what details you have, these are the sorts of things you can do with the old seismograms. So magnitude recalculation is relatively simple. You just need the record and you can measure the amplitude and stuff like that. You do need to understand the instrument response parameters, but those are generally cataloged in most places. Refining the epicenter depends on picking phase arrivals, and that depends on the accuracy of the timing of the various instruments. Some of the instruments don't have well-reported time offsets, and so this can be problematic, although, again, each of these things sort of whittles off the number of records that are useful out of all the ones that exist. If you're confident in everything, you can actually do body wave modeling for the sub-events and moment rate. This requires also well-known instrument response. Surface wave modeling and comparing amplitude ratios to obtain the moment tensor of the earthquake and understand the focal mechanism. It's one of the important things that we want to do with, for example, the Changma earthquake, because of these ambiguities about how it started, which faults contributed, and how it propagated along the system. The other thing that's possible with the density of networks, for example, in Europe, is that to conceivably stack the seismic records in order to get a more robust signal of the event within a localized network. As I said, a lot of these parameters are, if not recorded directly on the paper seismograms themselves, they're recorded in station logs. The existence of these is somewhat inconsistent. So there's a hierarchy of information that's available. But nonetheless, it requires a great deal of work to go and collect all that information naturally. A lot of it is stored on physical paper copies. A lot of it is stored in microfiche and microfilm. But we've had the great fortune of a lot of great collaborators at the various observatories who've helped us access this sort of information. And then I've embarked on the long and arduous process of digitizing these. We use a correction algorithm, so the arm sweeping across the seismogram produces a curve that needs to be corrected for in order to get a digital time series of the actual ground motion. We use an algorithm that was developed by Galina Kulikova in order to correct them. And this is a sampling of some of the best records that I have from the Changma earthquake. 40 that I out of the 44 records, this is an example showing us showing what's available to work with here. Naturally, because of the sort of labor-intensive collection and digitization of these, it's an ongoing process, and it's a bit of a work in progress. So we're hoping to get results that relate the seismological parameters of this earthquake to what we can observe in the field geologically. This work has been done for other earthquakes, and a PhD student here, Chi O, has worked on the 1920 Haiyan earthquake, gotten nice results comparing reevaluated seismological magnitude using the actual digitized waveforms with what's observable geologically using high-resolution satellite imagery. So look out for her work and future things as well as this. So to wrap up what I've gone through here, we've been using satellite stereo DEMs. They're relatively inexpensive compared to LiDAR, which makes comparable resolutions of digital elevation maps. That captures terrain with sufficient resolution to map individual past surface ruptures, which helps provide the quantification of displacements in old earthquakes. The analog seismic records, fortunately, we now know that it's worth revisiting these old earthquakes to develop a more nuanced understanding of them than was originally used in their analysis and interpretation. So earlier, in the first half of the 20th century, and even the later half of the 20th century, analog seismic records were basically used to identify arrival times and seismic wave amplitudes. But by digitizing the records, we have access to a lot more information, and it's worth revisiting these older earthquakes that show some of the phenomena that we've recognized more recently to be important in seismic hazard and understanding the way that earthquakes propagate along fault systems. So although it's labor intensive to collect and digitize these old records, there's a great deal of information held in them that may help us relate the seismological properties of these older earthquakes with what we can observe in the field. I'll leave it there, and I'll remind everyone again that this talk and others are up on the COMET website. You can just search COMET Earthquakes, COMET Webinar, COMET INSAR, and you should get to the website. You can find the webinars there. And also, if you have any further questions, I'll take questions now. JD can see them. And you can also find me on Twitter at @Trimler. Thank you. So the question from Rich Walker here is, will I be able to see individual segments from the seismological data? And yeah, I think the answer is essentially no. The two ways that I'm expecting to be able to distinguish different events are twofold. So one of them is the focal mechanism of the earthquake, right? So there is a hint in the seismic records that you've got a small pulse with sort of opposite polarity of a larger pulse later. So there may be sort of an early sub-event, and you can pick that out of the source waveform. The other way to understand it would be to identify directivity in the propagation of the rupture, which would involve stations with opposite azimuths from the epicenter having sort of different durations of body wave training. And it's difficult to say with simply the processed seismograms that I have so far, because the stations aren't, although I have nice azimuthal distribution of them, they're not equally distant. So there's some adjustments. There's further steps of processing and analysis that need to be done. And so far, I've basically just got digital traces. Anyway, the question is, did different segments of the faults interact at depth? So understanding what happens at depth on any of these faults is several levels more complex than simply mapping them out and measuring things at the surface. But of course, it does stem from that fundamentally. So understanding the geometry of the fault trace and the geometry of the slip vector, all of that together helps us understand the structure of the fault. So, for example, with the Changma earthquake, let's find it. With the Changma earthquake, understanding the different kinematics of the different segments has its own implications for what the structure is at depth, whether the faults meet each other, whether the steps that we see in the trace are, propagate down to depth or don't, and the faults merge. So understanding the geometry and kinematics of those things are one of the first ways to understand what's really going on at depth. And in the case of the 1889 earthquake, the big Chile earthquake in Kazakhstan, the involvement of all three of those faults is, and especially the southern ones that are up at the crest of the mountain range, are highly suspicious of there being a deeper fault structure involved, much like we saw with the Kaikoura earthquake, where there's a hint that involvement of the subduction interface actually is what enabled this vast array of faults to rupture together in upper plates.
Another question from Scott of the ESPS. What level of protection in terms of magnitude do you think is attainable with your combinations of imagery and seismicity? In other words, what size of event will you have?
Yeah. So essentially things below a magnitude 7 are not really going to be detected by these methods. It takes about a magnitude 7 to produce substantial surface rupture on the order of more than just decimeters, and that's what is really going to be recognizable in satellite topography. And similarly, teleseismic earthquakes only really show up well on teleseismic recordings on the far side of the globe above the high 6s around magnitude 7. So intriguingly, I think the threshold is similar for both of these approaches. And I don't think that the combination of them inherently helps that very much, or at all.
Next question from Scott. Do you expect high resolution DM generation would be significantly more helpful? Alternatively, what's the lowest resolution confident works?
High resolution.
Do you expect higher resolution DM generation would be significantly more helpful?
I do. Part of the reason for that, in my conclusion slide here, I compare satellite stereo DEM with LiDAR, but in general, and I think a lot of us have worked with both, LiDAR is pretty much superior. And part of the reason for that is that you can get sort of properly sub-meter DEMs. And at this stage with satellite imagery, we're still at DM resolutions of around a meter. And for these magnitude 7 earthquakes, one of the reasons you can't necessarily see a magnitude 6.5 preserved in topography over the long term because the rupture lengths are small and the magnitudes of slip are small, on the order of 10 to 20 to maybe 50 centimeters. They'll be difficult to recognize in the landscape anyway, and the DEM resolution really hinders that a great deal when it's on the order of a meter. So higher resolution elevation models will give us much better access and help lower that threshold a great deal. It's also pretty crucial to get as high resolution as you can, simply to measure the offsets accurately, especially lateral offsets. Vertical offsets can be easy enough because there's a whole land surface that's separated and offset on both sides, but lateral offsets really require the identification of small-scale features that you can conclusively track, and the spatial resolution of a meter really inhibits not just the detection of the offset, but the detection of the feature itself that you're measuring offset of.
And maybe we should wrap up with these last two questions.
Okay, 2 and 1 questions.
Yeah, and they're kind of related to each other. So Farah asks, is there any effect of terrain mythology? I guess this is in reference to the complexity of the rupture on the surface. And Camilla from Kazakh asks, given the complexity of the ruptures you're seeing, how can we make appropriate hazard maps or anticipate the possibly complex earthquakes that could occur?
Oh, good. So 2 related questions. So, right, the first one was,
is there any effect of terrain mythology?
Is there any effect of mythology? I won't say no to that. I think broadly speaking, yes. At the scale that I've been showing you here, at the scale of these sort of large segments that are being involved together in the earthquakes, I don't think lithology is such an important control on the complexity of the ruptures, although the inheritance of older tectonic structures and sutures and what have you will play a role in guiding where there are fractures, weaknesses, and failure points for a rupture to propagate along. So I think there are 2 different scales. I think lithology has a really strong effect at really small scale complexity, but at the large scale, on this sort of like 50-kilometer scale, the segmentation of these ruptures is probably driven by factors other than strictly lithology. So hopefully that's a satisfying answer. It's difficult without I have no feedback in response here. So I'll just move on to the last question, which was, what are the implications then for how we cope with these things inside the appropriate? Yeah. So I would allude back to the cutting edge models, the USURF idea of understand that genuinely does try to explicitly incorporate the interaction and connectivity of different faults, and essentially evaluates how often any particular portion of a fault participates in earthquakes with others. In the USURF model, there are certain rules set about the geometric interaction of these faults and where ruptures can or cannot propagate. And I think certainly the 1889 Chalik example is informative here, because the rupture takes these greater than 90-degree bends and forms this real tight zigzag. And so you're getting essentially rupture back in the other direction. This is where also understanding any sort of propagation along this fault system that we can from the seismology really helps, because whether or not these all sort of move together or unlocked one at a time has a big bearing on what we infer the ruptures are able to do with our fault system. So understanding where an earthquake began and how the fault systems interacted will. Sorry, distracting. Lost my train of thought there. Basically, I think I'll distill it this way. There are 2 important facets to this. One of them is adding to our empirical record of earthquakes. So if we can demonstrate, look, this has happened in the past, then you can say, okay, it's possible for a rupture to break faults that have such and such angle with each other. Potentially with further study, you can give qualifications and conditions to that, like, well, in this environment, with these slip rates, with this sort of environmental structure around it, then that's possible. Nonetheless, just documenting that empirically is important. But I think then taking it to the next step and understanding the relationship between the faults that we can map and the seismological evolution of the earthquake itself, lends us a little more information about sort of physically how the rupture is propagating, and a bit more into the physical side of it, that will help form our theory of what can possibly happen. And with that, I'll conclude. Thank you all for joining and watching this.